Good day. On behalf of the Joint Industry Project Corrosion Inhibitors, I would like to welcome you all to the webinar series on precision in corrosion inhibitor selection testing for oil and gas applications, which we believe is the first right step. Precision is the first right step. That is the premises of this whole webinar series. The objectives of the webinar series are twofold. One, to promote broader awareness across the industry on precision. Specifically, the need for developing standard test methods with published precision, obviously for the corrosion inhibitor evaluation and selection. And walk through the process of developing standard test methods. We will be hearing from some of the association representatives in 2026 as to how the standard test methods are being developed. Standard test method development requires collaboration and coordination. This is not a one-person's show. It's a collective responsibility. That is one of the reasons why we are promoting this webinar series, because collaboration and coordination is critical to develop standard test methods with known precision. And once we have developed it, once associations have published it, what are the impacts, major impacts of the standard test methods on our industry practices, specifically on corrosion inhibitor evaluation. This is the broader scope of this webinar series. And we will also, in the webinar series, promote what we are doing in the joint industry project towards establishing standard test methods with known precision. The objective of the joint industry project are threefold. In phase 1, which was completed in 2024, we collected and summarized the existing best practices from owner-operators and chemical vendors. In total, I interviewed 226 people, and many of you participated. We really appreciate it. Based on those interviews, we identified that in the oil and gas industry, we use corrosion inhibitors for 23 different applications. Some of them are very traditional, for example, downhole tubular or oil production pipelines. Some of them are very recent, new, for example, carbon sequestration pipelines, hydrogen pipelines, and to also some extent, biofuels pipelines. So phase 1 collected and summarized the current best practices. In phase 2, based on those best practices, we developed step-by-step procedures representing the current industry practice on corrosion inhibitor testing. Again, 23 individual reports were written covering each one of the applications. In phase 3, which was started in December 2nd, we identified 8 methodologies that needs standardization. When we say standardization, we are talking about establishing the precision of each one of the methodology. Again, we'll be talking more about precision in the webinar series, but in the joint industry project, we are going to establish precision based on repeatability. Again, we will define what is repeatability later. So in this particular webinar number 5, we will discuss what does ASTM 202 rotating cage mean. Is it a single methodology or does it encompass multiple variations? Why we picked up ASTM 202? Because this is the only standard test method for corrosion inhibitor evaluation with known repeatability and reproducibility. That is known precision. Again, to set the stage, we are not doing this project just for fun. This is an industry requirement. Uh, we would like to lead this development. When we say we, I mean the whole industry. Oil and gas pipeline operators, owners, chemical suppliers, and consultants. Rather than these guidelines are being imposed by regulators or by insurance companies. If you look at the corrosion control strategies, they are broadly classified into four: materials, coating, external coatings, as well as internal coatings, cathodic protection, and of course, corrosion inhibitors. If you look at the level of standardization, the corrosion inhibitor evaluation is not up to the mark. Right now, the criteria we are using are very qualitative. Right now, there is no industry or regulatory requirement, but if we do not act on it, the regulators may impose something on us. So that is the reason why we started the JIP 4 years ago and why we are doing this webinar series. As we indicated earlier, when we do tests or activities, that should be carried out uniformly around the world. So that whether a person does the exercise in Australia or Antarctica, they should get the same, they should do it the same way. Towards that, the contributions of associations such as AMP, ASTM, ISO are very, very critical. And these associations are formed by a group of professionals like us. In 1940s and 1960s, a group of professionals established the NACE RP0169 for cathodic protection. Again, in the previous webinar, we heard about the history of NACE RP0169, which was a pivotal moment for cathodic protection. Similarly, for coatings, 13 ASTM standards were published in 1972 to 1978, and we still use all but one ASTM standard. Of the 13, we are still using 12 of them. And of course, for material selection, especially for sour service, everybody around the world follow MRO 175, NACE MRO 175, or ISO 1556. All these standards were established in 1970s, except for corrosion inhibitors. The first standard was published in 2009. That is not enough. We would like to have more standards published so that around the world, corrosion inhibitor evaluation is carried out consistently, confidently, with known precision. What do we mean by precision? Both ISO and ASTM define precision in the same way, even though the languages they use are different. For instance, ISO 5725-1 defines accuracy. Accuracy is how close a measurement is to the true or accepted value. The accuracy consists of two things: trueness and precision. Trueness is closeness of the mean of many measurements to the true value. Classic example is when we say sun rises in the east, actually it is not true. We are not even close to reality when we say sun rises in the east. Scientifically, sun doesn't rise. It is the rotation of the earth that gives the perception that sun rises in the east. So trueness may not be known at all. But according to ISO 5725, trueness is closer to the actual true value. The second part is precision. When we say sun rises in the east, we all know what it means. It is precise. When you look at the east side, in the morning, sun comes up. That is precision. So we all accept a statement consistently. That is precision. And the precision, according to ISO, consists of repeatability and reproducibility. Obviously, it is repeatability is closeness of the measurement to each other, regardless whether they are close to true value. So when we say sun rises in the east, we are very precise, but it is not true. So that is the definition of accuracy. Accuracy consists of trueness and precision. And there is one other thing is known as repeatability and reproducibility. Repeatability, ISO doesn't define, ASTM defines it. In terms of ASTM defines precision based on repeatability and reproducibility. Repeatability is the same person doing the same experiment using the same apparatus under the same condition and following the same procedure. That is repeatability. One person, same test. Reproducibility, different persons following the same procedure using the similar apparatus under the same condition following the same procedure. So repeatability and reproducibility are defined through precision. So you might ask, what's the difference between ISO and ASTM? ISO defines accuracy, which is trueness times precision. ASTM defines precision. However, ASTM also in their standard defines what is known as bias. Bias is closer to the trueness. So for practical purposes, for corrosion inhibited testing, what we are looking for is precision. We may or we may not get the trueness. That is a premises with which we are doing the lab testing to evaluate corrosion inhibitors. So now let us see how far we have achieved the trueness in precision. Trueness is one part of accuracy. I'm happy to note that Rich McDonald, one of the stalwarts in our industry, is also here in our webinar. And Rich was involved in this project that was conducted by CanMet in 1990s, which was an extensive project in which both lab experiments as well as field tests were carried out. Field experiments in Alberta and lab experiments in Ottawa in Canada. And then they compared how far the lab test mimics the field test, for which we defined logarithmic. If the logarithmic of lab to field is positive and it is close to zero, that methodology to a larger extent reproduces the field conditions in the laboratory. That is closer to the trueness. So the field is a benchmark, and compare that one with the lab testing. If the lab testing is a little more aggressive, but still it is closer to the field, that was ranked as number one. We do not want to have a lab methodology that fails all the corrosion inhibitors. That could be very aggressive, but it is not closer to the trueness. So that is ranked number two. And if the lab experiment underestimates the corrosion rate, that is, it qualifies the inhibitor in the laboratory, but the inhibitor failed in the field, which is not a good condition. So that methodology is ranked as three. And if it is far away from the lab, it is considered as four. So this is how in the 1990s JIP, Canmet and a group of experts defined lab experiments in terms of trueness. In that project, three field tests were carried out using six inhibitors. Three of them were continuous, three of them were batch inhibitors. In total, 12 lab methodologies were evaluated, both atmospheric pressure as well as elevated pressure. And all the comparisons between field and lab were done based on both general corrosion rate as well as pitting corrosion rate. That project made 68 individual ranking. And this is the ranking. Rotating cage became number one, followed by rotating cylinder electrode, jet impeachment, rotating disc electrode, which is not commonly used in the oil and gas industry, static test, and wheel test. So this JAP was completed in 1999, and several publications were made out of that JAP. To promote that, rotating cage was the number one methodology in terms of trueness. Around that period, ASTM formed a committee. Actually, Russell Kane, Russ Kane, started that committee in which Milan Bartas, at that time, NALCO, was a chair and I was a vice chair. And they took the CanMet outputs, findings, and they started developing standards. The first standard was published in 2002 as a standard guide, ASTM G202. And then standard practice in 2005. Standard test method was originally published in 2009. Reproducibility statement published in 2011. So in terms of definition, guide means it gives general guidelines. If you look at the standard guide, it may say you may do it. The temperature may be 30 degrees. It doesn't specify, it gives you option. Standard practice one level up, it gives you step-by-step procedure. And if you look at the standard practice, it uses the verb you should. The temperature should be 30 degrees C. The pressure should be whatever it is. So it gives very clear direction. But standard practice does not give you an expected result. The golden standard category is standard test method, which not only gives precision in terms of repeatability and reproducibility, but also it publishes a research report. That research report is based on round robin tests. And this is the research report on the outcome of the research report. Fundamentally, basically, it gives you under the operating conditions, what should be the corrosion rate, average, and what could be the allowed variation. Again, this was based on 10 laboratories from across the world. I know several laboratories which participated in the round robin also here in this webinar. So what does it mean? So the CanMet JIP established rotating cage to be accurate, there is trueness, and the ASTM round robin test established the precision. So rotating cage became winner both in terms of trueness as well as precision. That work was completed in 2000, I would say 11. 2009 was the first publication. 2011 was when the research report was published by ASTM. Now let us talk about some of the details of ASTM standards on rotating cage. When we say ASTM standard on rotating cage, it has a very clear geometry and number of coupon requirements. Even though we call it as ASTM rotating cage, it has got 8 coupons and it has a 2-gallon volume apparatus. So this is how the apparatus would look like, with 8 coupons with a hole on the top as well as at the bottom. This is a close-up shot of the coupon assembly. Again, note that there should be 8 coupons. 1 coupon was removed in this photo. And again, note there is a hole at the top and hole at the bottom. These are very, very specific geometry when we say ASTM rotating cage. And again, if you go to any of the ASTM standards, G170, 184, or 202, the geometry or the apparatus size and dimensions are exactly the same. When you say rotating cage, we need a rotating cage which holds a coupon. We have to have a shaft which rotates it. Obviously, there should be a gas inlet and outlet, a motor that controls the rotation speed. This has been well defined in the ASTM standards. Again, note that the rod on the rotating shaft should be housed at the bottom so that it doesn't wobble. And many times I get calls saying that we did the rotating cage, we have got some erosion behavior. The first question I ask them is whether your shaft is aligned at the bottom so that there is no wobble. Again, this is specific to ASTM. Again, ASTM specifically tells about the rotating cage width, which is 8 centimeter. You can do 6 centimeter or 4 centimeter, but ASTM G170 recommends 8 centimeter. It specifies the length of the rotating cage, 8.5. It specifies the length of the apparatus, which is 40 centimeter. And it specifies the diameter of the apparatus, which is 15 centimeters. Very, very specific. These specifications are very, very important to follow if you are going to say that you followed ASTM standard. And again, we talked about the geometry. ASTM G170 also talks about how the flow pattern changes as a function of rotation speed and the volume. In the ASTM rotating cage, distinctly, there are 4 zones. Zone 1 is homogeneous zone in which as we rotate, there's a vortex formation which increases as a function of rotation speed. That is the definition of homogeneous zone. The vortex grows as a function of rotation speed. And then as the vortex grows in length as well as in width, and beyond certain rotation speed, beyond certain volume, the vortex doesn't grow along the side. That is known as side wall affected zone. The third one is a top cover affected zone. As the vortex forms, it pushes the solution up and the solution reaches the top cover and afterwards it doesn't grow. Top cover affected zone. And finally, turbulent. If you have a high rotation speed, the turbulent penetrates into the rotating cage, into the coupon. It really creates aggressive both corrosion as well as erosion behavior. So when we say ASTM, you are talking about a particular geometry, and the flow pattern of that geometry varies as a function of four properties. One, the medium, whether it is water or sodium chloride or crude oil, whether the holes are aligned or not, what is the volume of the solution that was used, and what was the rotation speed. Four parameters. And again, ASTM provides this information in a tabular form. What are the homogeneous zone? What are the sideward affected? Top cover and turbulent. So when we say ASTM, we are specifically talking about one geometry. When we say ASTM precision, we are talking about ASTM geometry, one geometry under one operating conditions. Now let us see what are being used in the industry. These are some of the pictures I obtained courtesy of SET laboratories. Several people have several geometries, and they still claim that they follow ASTM standards. For example, this lab claims that it uses ASTM G170. We do not know the volume of the apparatus or the zones, whether it is homogeneous top cover affected zone. And again, if you look at the ASTM, the gap between the coupons is established. If you look at this one, there is a little higher gap between the test coupons. These affect the flow patterns, and these do affect the corrosion rate as well as inhibitor performance. Some labs use three coupons, two coupons, one coupon, and the cage size is different. Again, for those who know the history, the rotating cage was first invented in Germany by Professor Gunter Smith in 1980s. I think you might know some of the stalwarts like Gunter Smith and Rudy Hausler. They were the one who actually originally proposed the rotating cage geometry as a design. In their design, they had what is known as baffle. That is, it breaks the flow pattern. As a result, vortex doesn't form. This was the original design. In 1980s, for several reasons, Canmet removed the baffles to produce results that were closer to the field operating conditions. So again, you have to understand whether we have any extra features in the rotating cage assembly. They all affect the flow pattern, corrosion rate, as well as corrosion inhibitor performance. Before Gunter Smith developed rotating cage, there was the industry in 1960s and 1970s were following another geometry that is known as rotating probe. Some people may still call that one as rotating cage, but that is not true. The rotating probe, the major difference is that, yes, it has an assembly at the bottom which holds a coupon, but it does not have the top cover. If you look at the 1970s and 1980s, this is known as rotating probe. There are some good publications, both in German as well as in North America. So rotating probe is not rotating cage. Rotating cage has got top cover and bottom cover. These characterizations are important when we are standardizing it. To sum up, when we say rotating cage, ASTM rotating cage, there are three standards: G170, G185, and G202. And they all specify only one geometry, of which ASTM G170 prescribes or describes the flow pattern and how it varies as a function of solution volume as well as rotating cage, as well as rotating speed. So G170 is a guide. It talks about the flow pattern. G202 is a standard test method with known precision. That precision statement were developed based on one geometry under one test condition. So when we say precision of rotating cage, we are talking about ASTM one geometry under one flow condition. The applicability of ASTM 202, the precision of ASTM 202 to other geometries is not known. It doesn't mean that we can develop new standards, do round robin test to establish those precision. You cannot copy and assume that the precision established for a particular geometry will be applicable to all the geometries under all operating conditions. This is one of the common mistakes our industry does it. So that is kind of a summary of rotating cage. And we'll also quickly go through what we are going to do in the joint industry project phase 3. Again, as I said, we have got good sponsorship. We also got some additional funding from government source to hire students. And we are in a good shape to progress with this JIP. And also, thank you for all the 25 non-sponsors who contributed to the development of the scope of the JIP. Obviously, we are looking for more participants, more the merrier. In phase 3, as we indicated, we will standardize 8 methodologies. When you say standardized, we will develop standard test methods with known precision. We talked about 1 liter rotating cage, I believe, in webinar 2. And some people asked why we are standardizing the 1 liter rotating cage since we already have the ASTM 202. That was the reason why we talked about the ASTM 202 extensively in this webinar. So what we are going to do with 1 liter rotating cage in the JIP, again, a little bit of history. At this stage, ASTM 202 talks about 7.2 liter atmospheric pressure rotating cage apparatus. Only for that apparatus, we have the precision statement. What is the magic number of 7.2 liter? Actually, in 1990s, when Canmet started their JIP, many people were using 2 US gallon autoclave. As a matter of fact, at that time, only that autoclave was available, at least in Canada at that time. So 2 US gallon is equal to 7.57 liter volume. That is the total volume of the apparatus. And normally, when you do autoclave tests, you have a liner so that the autoclave is protected both from contamination as well as from types of corrosion, even though autoclave may be alloy or corrosion-resistant alloys. Commonly, labs use internal liners or some additional components. When we place this liner and additional components, the fillable volume became only 7.2 liters. Again, this is an autoclave. So when Canmet did the autoclave test, high pressure, high temperature, and compared that one with atmospheric pressure, they established the atmospheric pressure rotating cage of volume of 7.2 liters. It precisely matched with the autoclave 2-gallon US 2-gallon autoclave with liners. That is how 7.2 liter atmospheric pressure rotating cage geometry was established. And that's what ASTM took to standardization. However, the 7.2 liter volume is relatively large when you do regular corrosion inhibitor evaluation, especially during screening process. That is one of the reasons, one of the main reasons why we want to standardize the 1 liter rotating cage in the current JAP. Again, we did the industry survey. Some companies are already using 1 liter rotating cage, either with 1 coupon, 2 coupons, 4 coupons, or 8 coupons. And they claim that they follow ASTM 202. However, as we explained earlier, the 1 liter autoclave's accuracy in terms of trueness and precision is at this stage not known. Trueness compares of lab testing with field testing. Precision, repeating the same test under same condition. In JAP phase 3, we will standardize 1 liter rotating cage only in terms of precision. We may not know the trueness, but we are only going to focus on precision based on repeatability under one lab to start with. In phase 3, we will establish the flow characteristics, corrosion rate variation, how the number of coupons affect the corrosion rate as well as inhibitor performance, how the coupon geometry will affect. As I said, the 7.2 liters autoclave rotating cage, the accuracy or the trueness was established by Canmet in 1990s by comparing lab test with field test. So to understand how closely the 1 liter rotating cage will mimic the 7.2 liter rotating cage, we will establish the aspect ratio and understand how the trueness obtained in 7.2 liter rotating cage can be transferred into 1 liter rotating cage. That is slightly beyond the scope of JAP, but the JAP's focus is to understand the repeatability or precision of 1 liter rotating cage. So quickly, in terms of the whole summary of the deliverables of phase 3, for each one of the laboratory methodologies that will be standardized, we will write a step-by-step procedure. And in fact, we have already started it, and the sponsors are reviewing it. And for any new methodology that will be standardized, we will develop the blueprint. That blueprint will be made available to all the sponsors so that they can manufacture their own apparatus. We'll talk more about the solution composition in one of the future webinars, but establishing standard solutions, establishing procedures to prepare them, as well as saturating them with acid gases is very, very important in establishing precision. So we hope to develop standard solutions, at least 5 standard solutions for inhibitor evaluation. The phase 3's end game is to develop precision statement based on repeatability, that is based on one laboratory. And we will submit our findings after the confidential period is over to the ASTM or AMP to develop standard test method based on repeatability. ASTM can publish a standard test method with only precision based on repeatability, provided the reproducibility is established within 5 years. So the phase 3 will end with repeatability, and we hope that ASTM will coordinate round-robin test to establish reproducibility. Of course, sponsors will be active in coordinating these inter-laboratory studies that will be carried out after the completion of phase 3. Again, we talked about the sponsorship. For the new sponsors, if you join for all phases, it is $50K US. If you want to join only for phase 3, it's only 25K. And we also have a new category or a different category for third-party laboratories which are not associated with any chemical vendors. They can they need to pay only 25K, but they will get the report from phase 1 and phase 2, provided they commit to help us contribute recession statement in terms of reproducibility. In other words, they should also do some lab testing after the GAP is completed. That's all we have for this webinar, and I'll open the floor for discussion.